Now for this section, we're talking a bit about antiderivatives. I doubt that we have anybody who isn't, taking the LSU curriculum here. But if you are here from a different university, these section numbers reference James Stewart's Calculus and Early Transcendentals. Now, antiderivatives are pretty much just the undoing of derivation. Normally, we're given a function f, and I want to get to f prime. I want to derive things. Well, antiderivation is just working backwards. Given a derivative, can you find the original function? Well, we can. So, if f prime of x is equal to e to the x plus 2 square root of x plus a cosine x, find f of x. Now, whenever we're finding f of x, i.e. finding the antiderivative of a given, the antiderivative of a given function, if we're not given any other information, such as initial conditions, we have to specify that we're talking about the general antiderivative. So sometimes they just say, if f prime is this, find f. I'm just putting on this little extra parentheses to state that it's a general antiderivative. Sometimes a text is a bit more explicit in that they'll say, find the most general antiderivatives for these functions. It just depends on how the problem states it. But to solve this question, we just have to think, what did we derive to get these terms? So what we learned in class is that to find an antiderivative, essentially you can do the same thing like you do for derivatives and just find it term by term. So the antiderivative of this f prime is just going to be the sum of these three antiderivatives of these functions. So what would I derive to get e to the x? Well, this is something we learn in 1530, or just, your introductory calculus class. E to the x is the only function whose derivative is itself. Pretty interesting, right? Now, that gives us an idea about, okay, well, what is the antiderivative for the first term? Now we got to talk about the second. So, what we learned in class is that if I have a constant attached to a function of x, well, I don't have to worry about it. Essentially, I can just find the derivative, the antiderivative of the term involving x. In this instance, a square root of x, but this could be x to a power, such as 3 or 2. This could be just a plain old x. The important thing is that the constant shouldn't really affect my work here. Now, something that we should probably make note of is that the square root of x can be written as x to the 1/2 power. To get that as a derivative, you had to have had a higher power, because the power rule always reduces your power by 1. Okay, well, if I want to go backwards, I have to add back on that 1. So I take this x to the 1/2, and I'm going to have to add a 1 to it. Likewise, whenever we do the power rule, we bring down this power as a coefficient. So since I don't have a constant over here, I have to put that coefficient right there, right? Now all that is to say is that the derivative of 2/3 x to the 3/2 is going to be equal to x to the 1/2. And this is just from the fact that 1/2 plus 1 is 3/2. Okay, if I'm dividing by 3/2, we flip it, make the reciprocal. And then we have the second term's antiderivative. We'll just have to remember to multiply by that constant later. Now, last but not least, this is one that honestly should be pretty easy. We should know our trig derivatives like the back of our hands. What do I derive to get cosine? Just a plain old sine. All right, cool. So now, term by term, we have our antiderivatives. I'm going to go on to the next slide, so feel free to pause if you need it. Thus, f, the general f, is going to be the sum of all these antiderivatives. For the first one, I got an e to the x. For the second one, I got a 2/3 x to the 3/2. For the last one, I got a sine x. And this is the important thing whenever you're doing an antiderivative problem. When you're finding a general antiderivative, you always have to add c, a general constant. The thing about derivation is that a constant always vanishes. So if I'm trying to keep these functions general, I just have to say that, okay, well, there might have been some constant. It could have been 0. The constant could totally be 0. Nothing wrong with that. But it's just that it could have been 1. It could have been 2. It could have been your favorite number given, maybe like the square root of 37. Could have been that. This just, eliminates all possibilities, essentially. It says that there's a constant, whatever it may be. Now, at this point, all you can really do is just simplify. So that first term, you have an e to the x. Then I just multiply fractions here to get a 4/3 x to the 3/2. We got a plus sine x. We got a plus c. And that is your most general antiderivative. Now we'll go on to the next slide and talk a bit more about specifics. So what I said earlier should have sort of tipped y'all off, but if we're given a bit more information about this f that we're trying to find, such as initial conditions, we can actually figure out definitively what is this function. So suppose that f prime is equal now to 1 over x, right? Plus an x. And f at -1 is equal to 1. What we're going to do is we're going to find the specific antiderivative f of x. So the work in starting out to find that antiderivative is just like we do for the general case. Term by term, we have to think, what do I derive to get these terms? Well, this is a standard derivative that should be a bit familiar to us. If I take the derivative of the natural logarithm of x, specifically an absolute value, then I get 1 over x. Now, what would I have to derive to get x? Well, this is like x to the first power, so I know that what I had over here was x to the second. Reduced by 1, we're back to x to the 1. Now this 2 would come down as a coefficient, so that means that what's over here must be 1 over 2. So the antiderivative of our second term is 1/2 x squared. So in general, f of x is equal to ln of the absolute value of x plus an x squared over 2, and then there's some constant. Now, whether you write like this and you put the coefficient to the side, or you put x over the coefficient, it's all fine. I mean, they're the same thing algebraically. You should just write whatever way makes you comfortable. Now you might be asking yourself, why did I have to put that absolute value there? Isn't the derivative of the natural logarithm of just x also 1 over x? I mean, yeah, it is. Sure, totally, definitely is. But what should tip us off is that I'm taking in -1 to the function. So that means that my domain has to include negative values. Okay, well, since I have to include negative values, there has to be an absolute value there. If I didn't have that, then I would get domain errors. All right, great. And then, right now, I haven't used that extra information. So, keeping it general, we just put a C. But, since we know f at -1 is equal to 1, we can find the C. Well, f at -1 is also the same as putting in -1 anywhere I had x. So I have the natural logarithm of -1 plus a -1 squared over 2. And then C has no dependence on x whatsoever, so it just stays as is. Now, what you should know is that the natural logarithm of 1 is 0. And then because this is squared, this becomes a positive 1/2. So this is going to simplify to be 1/2 plus C. Now notice that these two are equal to each other. And so C is 1 minus 1/2. Well, that's just 1/2. And to be honest, I mean, I'd be fine if you gave me the work here, personally. Because you gave me the general antiderivative, and then you said, okay, well, C in this instance is 1/2. But if you want to be fancy, and just be a very explicit, thus, f of x is going to be equal to the natural logarithm of x in absolute value plus an x squared over 2 plus a 1/2. And that's how we get specific antiderivatives when we're given extra information. Now, I'm going to continue to the next slide. If you need to pause, feel free. Now, in real life, you may be wondering, okay, well, this is cutesy, but what's a real application of this? Well, one instance is particle motion. So, suppose a particle is moving with the given data. Acceleration is equal to 3t minus a 3 the initial velocity of the particle is going to be 3 again. And let's say the initial position is 0. Now, to be honest, all right, well, we can get some units down here. So let's say that AT is in centimeters per second squared. Then the units of our velocity would be centimeters per second. And our position would just be centimeters. So if this connection isn't really clear, it's something that'll probably make a lot more sense once ever you start getting into an actual physics class or even a chemistry class. But especially physics, because you'll be dealing a lot more with just physical phenomenon. It'll make more sense in that, okay, whenever we're taking derivatives in time, our units are divisible by time. Take another derivative, we're divisible by time squared. These are things that relate directly to the difference quotients that we've been so used to in a mathematical setting. Now, given this information, we have to relate it into the realm of mathematics. So first things first, S of t is what I usually use to denote position. And you can think of that as your original function f. V of t is what I usually use to denote velocity. You can think of that as f prime, the first derivative. A of t is what I usually use to denote acceleration. That's sort of like our second derivative. So, what we're given is this boy right here, AT. And, oh, I forgot to even write the goal of the problem. So we want to find the position of the particle after t seconds. Now, what I'm about to say is probably going to make a lot more sense. So basically, with the given data at hand, we want to go back from A and get to S. Well, we got to figure out how to do that. Well, in a mathematical setting, essentially I'm getting from f double prime to f prime. What that means is that we're taking an antiderivative. So now, term by term, let's just take our antiderivative. All right, the 3 I'm just going to multiply at the end, but what's the antiderivative of t? You just saw it the last time, t squared over 2. If I have a constant, and I derive and get that constant, essentially I just had the variable there. If you derive c times t in this instance, you're just going to get back c. That's one of our elementary derivative rules. Now we have to keep it general so far, so we have to put a plus c. But we know some information about velocity. We know some a value that it takes on. Because I know initial velocity, I know v at what value. I know v at 0. And I know it's equal to 3. Okay, well, when I plug in t to be 0, the first term goes away. Same thing with the second. Okay, it turns out that c is actually equal to 3. Yep, just fine and C. All right, well, great. That lets us specify a specific V. So Vt is 3/2 t squared minus 3t plus 3. All right, great. So now that we have this information here, we can go on to the next thing. Now all I'm doing right here is just rewriting what we had before. So I know velocity, but I didn't want to stop here. I wanted to get to position. Okay, well, we can do that. We just do another antiderivative. Now, term by term, let's just take it. 3/2, leave it alone. We're just going to find the antiderivative of t squared. Well, that means that I had a t cubed because I reduced the power by 1. Well, I'd have to divide by 3 to take care of that pesky coefficient. Okay, great. We got the first term. We already did t. It's not really that interesting. And we already did 3. It's not really that interesting. But I have to take care of that constant there. Now, just like initial velocity is v at 0, what do you think initial position is? It's s at 0. And I said that s at 0 was 0. Whenever I plug in all these terms, okay, well, the first term vanishes. I mean, so does the second, even the third. So in this instance, c is actually equal to 0 identically. Thus, st, okay, we can divide these two, is 1/2 t cubed minus a 3/2 t squared plus a 3t. And this models our position after t seconds. Now, this isn't our only real-world application. Instead of talking about just particle motion, we could talk about object propulsion. Throwing a ball in the air, seeing how high it gets and when it's going to hit ground, finding its position function. If you don't even want to talk about the realm of position functions, we could say that if f prime models marginal cost, find our cost function. And in a real world setting, essentially, that's just meaning that if you have enough accurate data to sort of estimate how much your costs are going up as you produce another unit and then another unit, then you can use that data to sort of model your general cost function. And so even if you're only doing production, say at 100 units, with the given data, you might be able to estimate, okay, well, if I want to produce 500 things, how much would this cost? So the important thing is that antiderivative problems, they don't have to stop at just basic, here's an f prime, find an f. It can also be something like, here's an acceleration, find me position. Here's a marginal cost, find me cost. Marginal revenue, find me revenue. Marginal profit, find me profit. A lot of instances that we can talk about just using the fact from the real world definition of derivatives in the sense of economics and the natural sciences.